Great, thank you. Yeah, this is a project that's actually funded through the Instrument Incubator Program, but it's an instrument concept demonstration, so it's very low TRL stuff. And I want to acknowledge that the real effort being done here is being done by my grad students. Mohammed Mustavi has graduated and moved on. He's working at JPL now, and currently I'm working with Miriam Salim and Puneet Yogananda, whose materials are being presented here. So next slide, please. All right, the issue is snow on the ground. It has been identified by the decadal survey to be an issue of most importance, and that's because even though we have a multitude of different ways of attacking the problem, we're not really satisfied yet with how to get global coverage for this really dynamic covering of the ground. And so NASA has been involved, for example, with SnowX, a large-scale snow experiment going on for at least 5 seasons, trying to figure out what are the optimal approaches to addressing just several questions about snow, such as albedo, but in particular, just what is the water equivalent of the snowpack that's on the ground? How much water will we have when it melts? Seems like it'd be a really nice thing to know. Wideband autocorrelation radiometry, I'm developing it. ESTO is supporting it as another tool in the toolbox. It's passive microwave, which definitely has a very long heritage, and we know the advantages of that. The passive being low power and low cost, the microwave being all weather. But we're working at a different wavelength region, much longer wavelengths, and as a result, what you get is a deterministic observable, and this means that there's no algorithm calibration that's required for it. Next, please. And this is what I mean by that. What we're looking at is the coherent effects of a slab, and the snowpack can act like a slab. The emission from underneath the slab comes up and transits the snowpack and heads towards your radiometer. But if the wavelength is long enough, the interfaces are smooth, the scattering within the pack is small enough that you can actually get multipath heading up, and that delayed ray that comes up, even though its source is noise, it's actually a reduced amplitude and time-lagged copy of the original ray. And that produces both coherent construction at some wavelengths and destructive interference at other wavelengths. And it also has a very characteristic time lag, which reveals how thick the snowpack is. What we're demonstrating with this is we know that the signal exists for lake ice. We're looking at the much more subtle signal for snow. And we're also looking at a novel receiver architecture that actually enables much more rapid measurement than what we're currently doing. Next, please. So here's the part of the project where we're actually making measurements of the snowpack using our waves that we had done for demonstrating it on ice. It's basically a radiometer front end connected to a spectrum analyzer. And from the spectrum analyzer, you come up with the power spectrum, inverse Fourier transform, you get an autocorrelation function. And where the local maximum happens of the autocorrelation function, that's the time lag that reveals how thick the slab is. And what we're seeing here is some measurements from this past winter in mid-February. The color schemes on the plot is going from the colder temperatures to the warmer temperatures, including temperatures that are rising above freezing, at which point absorption in the snowpack gets large enough that you would not see any of that coherent effect anymore. And indeed, that's what we're sort of seeing in the autocorrelation functions that we've been able to produce from the data. You can see that the colder days, we actually have some signal. It's about at the place where we'd expect it to be. In the warmer days, it's not present. It's getting buried back into the noise floor of the autocorrelation. Next, please. For the rapid measurement, that's a spectrum analyzer measurement. It takes minutes, at least as long as this presentation, just to get a single measurement. To get more rapid measurements, we're looking at trying to collect the entire bandwidth at once instead of one narrow little resolution bandwidth at a time. We're doing it with sub-Nyquist sampling using two different clocks that are both slow, but they have a slightly different period. And the period difference is enough that the difference, the sampling time walks over the entire span of all the different lag times that we'd be interested in. And so in this little diagram, we've got a 100 megahertz clock and driving a phase lock loop producing a much more slightly slower clock that's different by 0.2 of a nanosecond, sampling the waveform as you can see down on the bottom that produces a walking set of correlations of your measurements. So next, please. At these low frequencies, about a gigahertz, you have a lot of RFI. And so what we need is a wide frequency range on the order of a gigahertz bandwidth, but not that much noise bandwidth. We can actually get away with a lot less noise bandwidth. So one way to deal with that complexity is that we built a microwave circuit equivalent of a Fabry-Perot interferometer. And not just that, but by incorporating a phase shifter, which is actually currently a commercially available part that you put in there, as you walk the phase around 360 degrees, you can actually walk the comb back and forth over the frequency span, as you can see in the figure. The approach is to make measurements of the total power coming through, and where the power is minimized, that is a point where the RFI is also being minimized. And unlike traditional radiometry, because we're looking for a time lag and not looking for a magnitude like a brightness, we can sustain quite a bit more RFI in our measurements and still get pretty decent results out of the whole thing. Next, please. So just to sort of outline a couple of the steps that we've been doing, we're looking at a receiver architecture for making these passive measurements of these cryogenic materials, snow and ice. The secret is using a longer wavelength so that we're sensitive to its macroscopic properties rather than to the scattering of its microscopic properties, like the grain size or the correlation length of the particles within the snow. We were sort of just about to start doing final integration and test when, the same theme as all the other presentations, COVID happened. We're hoping to get that done this summer, and that'll help us get to a point where we'll be able to demonstrate that it actually mitigates RFI. We've done a lot of simulations on that showing it works really well. The next step ahead, beyond this concept demonstration, is to develop a low SWatt receiver, eventually getting to a point where we can go airborne, produce images, basically measurements fast enough that we can actually have overlapping images. And at that point, we can start looking at the next attempt, which is actually doing some disaggregation on these images, because the footprints will be somewhat large. My final slide, I guess. Thank you very much, and especially thank you to ESTO for support. That's just a picture of the field site where we took our measurements this past winter. And that concludes my talk.